So these index nodes or inodes are usually stored on the disk whenever an inode is needed. In that case, it will be transferred or copied from the disk into the main memory when it will be called an in-core inode. So as we have said that as long as the inode remains on the disk, it contains various informations. For example, ownership information, that is who is the owner of the file. It also contains information about group ownership. It contains the access right permissions, that is whether the owner or the group or any other user of the system has got the read permission, write permission and execute permission, all those things. Then it also contains information about the access time, when the file or the directory was last accessed, or when it was last modified, or when the inode was last modified. Then it also contains information about size, what is the size of the file, and it contains an information about where on the disk different parts of the file are stored. So that is what is called inode table of contents. So these are the informations which are usually stored on the inode as long as the inode is in the is on the disk. Now inode is copied from the disk into the main memory when it will be called an in-core inode following an, say for example, an open command. So if you want to open a file, in that case the system has to search the inode corresponding to that file from the disk and copy that into main memory. So this in-core copy of the inode contains a number of other informations in addition to the informations which are available on the disk inode. So the first information, so these are the informations on the in-core copy of the inode. So the first information that will be present in in-core inode is what is the status of the inode. The status can be the inode is locked, that is currently the inode may be used by some process. So in this case the inode will be locked, so that if any other process tries to access the same inode, in that case that process has to wait until and unless it is unlocked by the process who has already acquired the inode. The second information that will be present in the status field is that one or more process is waiting for this inode to become unlocked. For the inode to be free. Free or unlocked. I won't say free because in case of inode the term free means something else. We'll come to that later. So I'll put it as unlocked. Okay. Then third information in the status field will be whether the disk copy of the inode and the in-core copy of the inode is different. Because if the inode is modified while it is in the main memory, in that case obviously it will be different from the disk copy. So even that information, that whether the inode is changed or not, is also present in the status field. So that if this in-core copy of the inode is to be overwritten by another inode, in that case if the previous copy was changed, it has to be saved onto the disk. Then the fourth information that has to be present in this is whether the file corresponding to this inode is changed or not. So all these informations are to be present in the status field of the in-core inode. These informations are not there on the disk copy. Then the other information, the other field you have to have for the device number of file system. From which this inode has been copied into the main memory. Okay. Then you have to have a field for inode number itself. Inodes are numbered by integer numbers. As long as the inodes are on the disk, you don't need an inode number because on the disk they are stored sequentially. Inode number 1 will appear first, followed by inode number 2, followed by inode number 3, and so on. And these will be stored sequentially on the blocks which are meant for storing the inodes. So in the disk layout, we have said that initial blocks are called boot blocks, followed by super blocks, followed by inode blocks. So in the inode blocks, all the inodes will be stored sequentially according to inode number. So I don't need specifically any inode number field in the disk copy of the inode. Okay, because they are stored sequentially. But when you are copying this into the main memory, in that case, that sequence may not be maintained, because I may not need inode number 1, but I need inode number 5. After that, I may need inode number 2, and so on. So the inodes will be copied into the main memory from the disk as and when it is required, and in which case it can never be guaranteed that they will be stored only in sequence. So I have to have a specific field in the in-core copy, which is the inode number. Okay. Then other fields will be pointer fields. These in-core inodes are maintained in the main memory almost in the same way in which the buffer cache is maintained. So as we have seen that in case of buffer cache, we maintain two types of queues, a set of queues which are called hash queues, and there is another queue which is a free buffer queue or a free buffer list. A buffer may be simultaneously present on a hash list and also on a free buffer list. Similarly, in case of inodes, I can have, in fact, there are similar two kinds of lists. We will have a set of hash lists. So inode with a specific number will be placed onto the corresponding hash list, which will reduce the search time for the inode. Okay, and simultaneously, when an inode is free, it will be placed also on the free inode list. And in this case, in case of inodes, the concept of a inode to be free is different from the concept of a buffer to be free. We'll come to that later. Okay. We'll also have an additional field which is called a reference count field. The reference count indicates that how many instances of the same inode is active simultaneously. So it is like this, that suppose a process opens a file for some reading or writing operation. Okay. Then while the file is open for some process, maybe another process also wants to use the same file. So that process will also open the same file. Usually what we need is, whenever a process wants to open a file, I have to search for the corresponding inode from the disk, copy the inode from the disk into main memory, when it will become an in-core inode. Okay. Now, if the first process opens a file, in that case, for the first process, the corresponding inode has already been copied into the main memory. Now, if the second process also wants to open the same file, in that case, it will find that the corresponding inode is already present in the main memory. I have an in-core copy of the corresponding inode. So this inode need not be copied from the secondary storage to main memory once more. Rather, what is done is, you just increment the reference count field. Okay. So when you increment this reference count field, this itself indicates that for the first time, when a process opens a file, the reference count field will be set to 1, indicating that there is a single instance active for that particular inode. When the second process also opens the same file, in that case, you search for the in-core copy of the inode, find the in-core copy, and once you get the in-core copy, you simply increment the reference count field by 1, which indicates that two processes are working on the same file simultaneously, or I have two instances of the same inode simultaneously active. Okay. Now here comes the difference between an in-core copy of the inode and the buffer cache. Here I said that when I say an inode to be free is different from a buffer to be free. In case of buffers, we have said that whenever a process wants to use a buffer, firstly it has to lock the buffer, use it. As long as the buffer is being used, the buffer remains locked. So it will be out of the free buffer list. The moment the process finishes its work on that buffer, it will unlock the buffer and the buffer will become free and it will be returned to free buffer list following LRU technique. Okay. Now similarly, in case of inodes, whenever a process wants to use a particular inode, we have just said that when the file is opened, the disk copy of the inode is copied into the main memory. After that, the inode is going to be referred quite frequently, because for every single byte you want to read from the file, you have to refer to the inode. Okay, because it is only from the inode I can get the disk address of that file. That is the inode table of contents. So for any read or write operation which has to be performed on the file, I have to refer to the inode. So consider a case that for a particular inode, two instances of the inode are active simultaneously. That means there are two processes who are working on the file simultaneously. Okay. Now one process closes the file. If one process closes the file still is open for another process. That means the reference count field is not equal to 0. Okay. And while the reference count field is not equal to 0, I cannot put this inode on the free inode list. Because when it is on the free inode list, then there is a possibility that this in-core copy of the inode may be overwritten by another inode from the list. That the concept is similar to free list buffer. So what the first process does is, the moment it closes the file, simply the reference count field is decremented by 1. But the inode will not become free. It may be unlocked. So whenever a process wants to read a particular byte, it will refer to the inode for getting the disk address. Okay. So for getting the disk address, it has to lock the inode. Once it accesses the disk address from the inode table of contents, it will unlock the inode. But that does not mean that the inode has become free. Inode is only unlocked. Because until and unless the file is closed, the corresponding the same inode will be referred again and again. So I cannot remove it from the info copy. So that is the difference between a buffer cache and an inode. It is unlocked does not mean that it is free. It is free only when the reference count becomes 0. That means all the active instances of that corresponding inode has been closed. Okay. So only when the reference count is equal to 0, the inode becomes free, and now it can be put onto the free inode list. And once it is on the free inode list, it is always possible that the inode will be overwritten by another inode from the disk whenever such a situation arises. Okay. Now let us see that what is inode table of contents. Lock means another process can't access it until and unless it is unlocked. Say I have two processes, a process P1 and process P2 who have opened the same file. Okay. Now suppose process P1 wants to read a particular character, say at an offset D1 from the file. So when this process P1 wants to read a byte at an offset D1 from the file, the process P1 has to use the inode, because the block address of this offset D1 of the file will be available from the inode only. That is contained in the inode table of contents. Okay. So what process P1 will do? Firstly, it will lock the inode, then get the block address, okay, and that will be followed by unlocking the inode. Okay. Now while process P1 is accessing table of contents to get the block address, process P2 cannot access the same inode. The process P2 will access the same inode only when it is unlocked by process P1. But this does not mean that the process P1 has closed the file. Process P1 has only accessed the inode to get some information. Okay, it has not closed the file. Similar with process P2. So only when process P1 will close the file, then only the reference count will be decremented by 1. Otherwise, the reference count is not touched. So if these are the two processes, P1 and P2, for which a particular inode is active, then the corresponding reference count field will be equal to 2. Okay. Once process P1 closes the file, reference count field will be decremented by 1. So now it will be 1. But still the inode is not free. It may be unlocked. So because it is not free, it cannot be put on the free inode list. So only when process P2 also closes the file, again the reference count field will be decremented by 1. It will become equal to 0. And now we know that the inode is not active for any of the processes. Okay. So only when the reference count becomes equal to 0, you can put this inode on the free inode list. Otherwise, you cannot. Now, what is this inode table of contents? As we said, that inode table of contents contain the pointers to disk blocks which contains different pages or different parts of the file. Okay. So in case of Unix system 5, and mostly that is followed, inode table of contents has a particular format. Okay. So I'll put it as inode table of contents. The table of contents has got 13 entries. Numbering from 0 to 12. Okay. So 0, 1, 2, this is 9, 10, 11 and 12. Okay. Now each of these entries contains some block address. The address of the block which contains part of the file. Okay. So out of these 13 entries, the first 10 entries are direct pointers. This is a single indirect pointer, this is a double indirect pointer, this is a triple indirect pointer. Now what does this direct or indirect pointers mean? When I say that this is a direct pointer, it means that the 0th entry in the inode table of contents that contains the address of a block or the number of a block which contains the file data. This contains file data. Okay. So all these entries from 0 through 9, they all contain the addresses of the blocks which contains file data. That is why they are called direct pointers. Okay. This entry number 10, that is a single indirect pointer. Single indirect pointer means it contains the address of a block which does not contain the file data, but rather it contains a set of pointers. Okay. Each of these pointers point to a block which contains the file data. Then the next entry, that is 11th entry, it is double indirect. Double indirect means that this entry contains the address of a block which contains a number of pointers okay. Each of these pointers point to a block which again contains a number of pointers. Pointers means addresses, and in this case these are disk block addresses. Okay. And these pointers in the second level, they point to blocks, they contain addresses of blocks which contains the file data. Okay. Similarly, in case of triple indirect, this contains the address of a block that contains a set of pointers. Each of them points to a block which again contains a set of pointers. Each of them will point to again a set of blocks which again will contain a set of pointers. Like this. Okay. And finally, these pointers point to blocks which contain the file data. Right? So this is what is meant by direct pointer, single indirect pointer, double indirect pointer, and triple indirect pointer. So in case of direct pointers, the pointers are pointing to blocks that actually contain the file data. So these entries from 0 to 9, the first 10 entries in case of inode table of content, they are the direct pointers. The next entry, that is 10th entry, is a single indirect pointer. So this entry points to a block which in turn contains a set of pointers. Each of them points to a block that contains the file data. This is a single indirect pointer. So this points to a block containing the set of pointers. Each pointer points to another block that contains a set of pointers. Each of these pointers point to file data. And similarly for triple indirect pointer. Okay. Now find that having this type of architecture in the inode table of contents, the size of a file can be very large. Okay. It is simply because if I assume that on a file system, every block is of size say 1 kilobytes. So block size is 1 kilobyte. Just to see that how big a file can be following this table of contents. So every block on the file system on the disk is 1 kilobyte. And if I assume that for addressing a particular block, that is address of a block is the 4 bytes. Address of block that takes 4 bytes. So if I assume this, in that case you find that every block can contain 256 number of pointers. Isn't it? Because the block size is 1 kilobyte, address of a block takes 4 bytes. So every block will contain 256 pointers, right? Now coming to this inode table of contents, following the direct pointers, if I only follow the direct pointers, what is the maximum size of file? No. Every block is 1 kilobyte. Direct pointers point directly to data blocks. That is 10 kilobytes. Okay. So simply following the direct pointers, I can access a file size of 10 kilobytes. Okay. Then following single indirect pointers, single indirect pointer points to a block which contains the set of pointers. In this case, I can have 256 number of pointers. Using 256 pointers, I can point to 256 blocks which will contain the file data. Okay. So following the single indirect pointers, I can access 256 kilobytes of file data. Because through this I can access 256 data blocks. Okay. So following the single indirect pointers, I can access 256 kilobytes of data. Okay. Following this way, when you come to the second indirect, you find that this points to a block which contains 256 pointers. Each of these 256 pointers points to blocks which again contain 256 pointers. Each of these pointers will point to 1 kilobyte of data. That means following this double indirect pointer, I can access 256 into 256 kilobytes. Okay. So using the double indirect pointer, I can access 256 into 256 kilobytes. Okay. Following the same logic, using the triple indirect pointers, I can access 256 into 256 into 256 kilobytes. Okay. Now if you consider this field alone, the triple indirect pointers alone, what is the file size that I can have? 256 means 2 to the power 8, 2 to the power 8, 2 to the power 8. That means 2 to the power 24 into 2 to the power 10. Each of them is kilobyte. That means I can access a file of size 2 to the power 34 bytes, which is nothing but 16 gigabyte. Okay. So using only this triple indirect pointer, I can access 16 gigabytes. Okay. Now if you add these, it will be much more than 16 gigabytes. So if I follow this format of this inode table of contents, in that case, the maximum size of a file that can be accessed is more than 16 gigabyte, and I think that is sufficient for any application that we can think of. Okay. So what are the operations that are to be done? Whenever any process wants to make use of any file, it has to get the inode number of that file. Okay. Once it gets the inode number, the inode has to be read from the secondary storage, put into the main memory when it becomes an in-core copy of the inode. Now once it is there in the in-core copy in the main memory, then I can check the permission fields, whether whatever operation that I want to perform on that file, I am permitted to do that on. If I am permitted to do that, in that case I can do the required action on that file, and for that I have to access different data in the file, and for accessing different data I have to check I have to access the inode table of contents. From the inode table of contents, I get the addresses of different data blocks, okay, and using those addresses, I can read the data block or I can modify the data block. Okay. So this will be the sequence of operation that will be performed during any file operation. So first thing that has to be done is I have to get the inode of the file that is required. Okay. So as you have seen, in case of buffer cache management, that whenever a process wants to read any data from the secondary storage, it first checks in the buffer cache whether the data block is available in the buffer cache or not. If it is available in the buffer cache, it does not have to go to the secondary storage for reading. If it is not available in the buffer cache, then it has to get a free buffer, okay, a free buffer which will be used for loading the new data block from the secondary storage that is required. And that algorithm we have said as get block algorithm. Okay. So similarly, in case of inodes, whenever a file is to be opened, I have to know that what is the inode number of the file. How to get the inode number, I will come later on. Now for the time being, let us assume that I know the inode number of the file that is to be opened. Okay. So the first operation that has to be done is I have to check in the in-core copies whether the inode is already present or not, because there may be situation that the same file was opened by some other process before, in which case the inode will be available in the main memory. Maybe the inode is locked, but it is available. Okay. So first, what we have to check is whether the inode is available in main memory. If it is not available in main memory, then we have to get a free inode. Free inode means the reference count field is equal to 0. So then I have to get a free inode, which is to be overwritten by the new inode that is needed. Okay. So the algorithm will be something like this. We'll put this as algorithm I get, that is getting an inode. Input to this algorithm will be the file system inode number, okay, and the output is a locked inode which will be given to the process that is requesting. Okay. So I can write an algorithm in the same manner of get block algorithm. So I'll write while not done, if inode in inode cache. So this is in-core copy of the inode. So first I have to check whether the inode is available in the inode cache or not. So if the inode is in the inode cache, then there is a possibility that the inode may be locked. Okay. So first we have to see is if inode locked. So inode is available in the main memory and the inode is locked. So the process has to go to sleep mode, sleep on event inode is unlocked. So here I am not saying inode is free. Of course, inode becoming free means inode is unlocked. But inode is unlocked. Unlocked does not mean that the inode is free. Okay. So the process has to go to sleep and the kernel will continue. So this is what we have to do in case inode is locked. If the inode is not locked, then again I can have two possibilities. The inode may be on the free list or inode may not be on the free list. Okay. So first I have to check if inode is on free list or not. Okay. So if the inode is on the free list, that means the reference count was equal to 0. So all the processes who were using this inode before, they have closed those files freed the inodes. Now this inode is again needed by some other process, and fortunately the inode has been found in the in core, in the main memory. Okay. So if the inode is on free list, in that case what has to be done is the inode has to be removed from the free list, because it will not remain free anymore. One process has requested for it. And after removing this from the free list, what I have to do is, because now another process has made this inode active, so now the reference count field has to be changed to 1. Earlier it was 0. Okay. So what I have to do is increment reference count field. Okay. And after that we have to return the inode to the process who has requested for it. Okay. So these are the operations to be done in case the inode is found in the inode cache. Okay. The next stage will be if the inode is not found in the inode cache. Okay. So if the inode is not found in the inode cache, in that case, I have to look for a free inode which will be used for loading the disk copy of the inode. Okay. Now here again the algorithm differs from that in case of buffer cache management. In case of buffer cache management, we have seen that if the free buffer list is empty, then the process goes to sleep mode. Because in that case, it is quite likely that some buffer will be made free by some of the processes, because buffers are not always used. They are only used during the process of transferring the content of the buffer to the user area, or from user area to the buffer, or from buffer to disk or disk to buffer. No processing is done in the buffer. Now, in case of inode, if the free inode list is empty, that means all the inodes are active by some process or other, and there is no guarantee when the inodes will become free. Okay, because until and unless the file is closed by the process, the inode cannot become free. So in this case, instead of putting the process in sleep mode, because the kernel does not know when the inode will become free, it may so happen that the process will remain in sleep mode forever. So instead of putting the process in sleep mode, you give an error message and terminate the process. Okay. So here we check that if no inode on free list, then you return with an error. Okay. Otherwise, if there is an inode on the free list, then that inode can be used for loading the new inode from the disk. Okay. So in that case, what you have to do is remove new inode from free list, reset inode number and file system, so that it gets the new updated value. Okay. Then earlier, because the inode was having some other disk copy of the inode, so it was put in some hash queue. Now it gets another disk copy, so it has to be put in the new hash queue, the new appropriate hash queue. So we have to remove inode from old hash queue and put in a new hash queue. Okay. After that, what we have to do is the read then we have to read disk inode from the disk, okay, and put this disk inode into this new in-core inode. And for reading this disk inode, the algorithm that has to be invoked is the block read algorithm that we have said in case of buffer cache method. Okay. So using this block read algorithm, because reading an inode is nothing but reading a block from the disk. So you make use of this block read algorithm to read the block containing that requested inode and put this inode into the new inode. So for that, what will be the operations done? Following block read algorithm, the block containing the inode will be placed into a buffer cache. You filter out from the buffer cache and put that into in-core inode. Okay. After that, what I have to do is I have to initialize the inode. And what does this initialization mean? Because this inode is being opened for the first time. Even if it was opened earlier, but all the processes who had opened earlier, they had closed all the files. That is why the inode could have gone to free list. Okay. So I have to initialize the inode. That means the reference count field in this inode has to be made equal to 1, indicating that there is only one instance of the inode which is currently active. Subsequently, other processes may also open the same file when the reference count fields will be incremented accordingly. Okay. And after doing all these things, we have to return the inode to the process who has requested for it. Okay. So this will be the sequence of operations whenever an inode has to be found for some process following some read operation, read statement of some file. Okay. So as we have seen that getting an inode, what will be the steps? Then similarly, we can have a number of steps which will be performed while freeing an inode or releasing an inode. I will not say freeing an inode, rather I will use the term that release of inode, which will be done following closing of some file. So a file which has been opened by some process, the process wants to close the same file. And while closing the file, the process will release the inode. In that case, it will become free. If all the processes releases the inode, then the inode becomes free.
So the idling doesn't mean it's like you want it to be free. I don't want it to be free.
Yeah, that will be taken care of by the iRelease algorithm itself. iRelease algorithm will check what is the reference count field. The moment it finds that the reference count field has come down to 0, the inode becomes free. Okay. So we'll put it this way. We'll write the algorithm as I put. Okay. Obviously, the input to this algorithm I put is pointer to the inode which is going to be released. Okay. So I'll write it this way. First operation that has to be done is lock inode if not already locked. Because you are going to manipulate some of the fields in the inode. Okay. So to avoid any discrepancy, so that other processes cannot make use of the same inode simultaneously while the inode is being modified, so first operation that is to be done is to lock the inode. Then next operation we have to do is, obviously because some process has closed the file or trying to release the inode, so I have to decrement the reference count field. Okay. After that you check if reference count is equal to 0. Okay. So if reference count is equal to 0, in that case the inode has to be put onto the free list. Okay. So before putting onto the free list, because there is a possibility that this inode may be overwritten by a new inode. a new disk inode. So I have to check. You find that when we discussed about, when we talk about the in-core copy of the inode, we have said about different pointers, different fields, okay, in the status field. That is whether the inode is changed or not, or whether the file has been changed or not. Okay. So if the inode is changed when the reference count is equal to 1, in that case this inode has to be saved onto the disk, and then only it will remain in the free list. Okay. So what we'll check is, if inode changed, then update disk inode. Okay. If the inode was not changed, then the disk inode need not be updated. And after that, you can put this inode on free inode list. So this can be done only if the reference count is equal to 0. Okay. So after this, whether the reference count equal to 0 or it is not equal to 0, because inode was locked, now we have to release the inode, or release inode lock. Okay. So this is the operation, steps of operations that are to be done whenever a process closes a file. While closing the file, it tries to release the inode. So the inode can be placed onto the free list only when the reference count equal to 0. If the inode is not, if reference count is not equal to 0, the reference count is only decremented, and after that the inode will be unlocked. Okay, so it does not go to the